Welcome back, students. So in this episode we'll try to figure out the time complexity for our BFS algorithm. Now again, I like to tell you something. See, for any algorithm the time and space complexity is very important, and if you're not able to, not only knowing them, it's important, but how you arrive at them. I've seen many good lectures on YouTube where they have beautifully explained the BFS or the algorithm, but they have not mentioned the time and space complexity. Although in some lecture they have just mentioned that what is the time and space complexity without arriving at it. Now for any algorithm, it's very important. If you are not able to convince yourself that how you arrived at this time and space complexity, there is no point of learning that algorithm. So with this, let's begin with the space and time complexity. So we'll see first the time complexity of BFS algorithm. So as you can see, this is the pretty much is the algorithm we have in our case, right? And so our time complexity will depend upon these operations only. So let's try to analyze them one by one. Now here in this step, what I'm trying to do, I'm just building a queue. Okay, so and that also will be done for the single time, right? So this is nothing but let's assume that it's a simple operation. It's going to take a constant time. O1 means a constant time because it is being constructed for the only once it will be constructed. So it will take some constant time for you. So I just mentioned it O1. Now next, what you will do in this step? Just NQ the start vertex on the very first position of an empty queue. So it will take a constant time, that is O1. Okay. Now we are here basically. This is our core logic. So before we proceed further, so one thing I hope must be clear to you that this operation for this BFS, it's running on each node one by one, right? So we have V vertices, so on each vertex it will come, right here each vertex will be popped out and will be evaluated like this wherever throughout this operation, but it will come right to each and every vertex. So it means this operation is definitely going to happen V times, right? This for loop will be called V times, each for every time for each vertex we have in this graph, correct? Second important point for this for loop is that this operation will take a constant time because it is what doing, checking that whether a particular vertex is visited or not, true or false. So it's a constant time operation. Again, enqueuing into the queue, that is at the end of your queue, is also a constant time operation. Fine. So this, now we know two things, that this for loop is going to be called for V times, and this for loop, what work this for loop is doing, it's also a constant time work. Now bear with me, I'm trying to help you analyze how to analyze these algorithms. So rather than just writing what is the time and space complexity, because BFS and DFS core of every graph algorithms. So once you are able to analyze this, any other time complexity for any other algorithm like shortest path will not be that difficult for you. So now we are now sure of two things, that this for loop is going to be called V times, and this for loop is going to do, every time this for loop is iterate, it is going to do a constant amount of work. Now the last step, that the key to this time complexity is that how many times this for loop is going to be called for each vertex, and that is very simple. So for example, in this case when we were at A, how many times this for loop is going to be called? The number of neighbors A has, that is the number of edges A has. In B, when we were on B, how many times this for loop is going to iterate? For 3 times, D, E, F. Although this condition will definitely be checked for A, although not this will not execute for A because A is already busy. But this for loop is going to iterate for 3 times. And what are 3? That is the number of edges B has. For A, it iterated for 2 times the number of edges it has. So now we are able to figure it out that this for loop, for each vertex, how many times it iterates? It iterates the number of edges each vertex has. So for all in all, that is for V times, how many times this for loop is going to iterate? It will be dependent upon what? That is the total number of edges this graph has. I'll repeat once again. So for each vertex, how many times it used to be called? The number of edges a particular vertex has. Now, if you try to analyze it for all the vertex one by one, it will be iterating how many times? Proportional. I'm not saying equal to, but proportional to the number of edges this whole graph has. Fine. So it means now, what will be the time complexity? So for this, it is O time E, and these are constant times, right? So this one is also basically O1. So how many times? So what is the complexity? O times E for this function. Now we are not done yet. Is there anything left? Yes, because in this algorithm we have to, first of all, what we have to do in the very beginning, we have to initialize also. So in initialization, what we have to do, we have to set all of these vertices to false, right? So how many vertices we have? We have V vertices. Let's say if we have V vertices, so we have to run a for loop, right, for all these V vertices, so that we set all these vertices as false, right? So how much, what will be the time complexity for that? Definitely O times V, because V is the number of vertices. We have to run this for loop for V times. So what will be the total complexity? So total complexity will be O times E plus O times V, which is nothing but E plus V. So this is nothing but equal to your time complexity in case of a DFS, right? So fine. So this was our time complexity. And now what will be our space complexity? So you can think of it. So how much space you need for this operation? Definitely maximum space. What will you need? What you will need? At worst case, what will happen? All these nodes will be in this queue, right? This could be the worst case, right? So all of these nodes are at the same time, they are in the queue. So that means the size of queue must be, to consider for the worst case, must be equal to the number of nodes. So it means what will be your space complexity? O times V, right? So this is the worst case. So normally you will not require queue of this size, because whenever you are pushing some nodes, you are also dequeuing. Fine. So this is the space and time complexity for your